All right, we're about to get ready to get started. This is Chuck Walburn doing a DirectX 11 technology update. After that, we have lunch, and then we have more DirectX 11 talks. We also have Xbox talks in the other graphics room. Lots of good talks for both sides. I hope you brought a friend to sit in both rooms. If not, now there will be all the presentations online too, hopefully. Anyway, take it over to Chuck.
Good morning. My name is Chuck Walburn. I'm an engineer at Microsoft. I've been doing these kind of conferences for several years now, and I lived through the joy of the Windows Vista and DirectX 10 launch, and I'm here again talking about DirectX 11 and Windows 7. Hopefully this time there will be fewer tomatoes thrown at us. So in 2008, we introduced the DirectX 11 API. We had a whole slew of talks from the Windows graphics team and from my team and others presenting on what was happening with DirectX 11. This, of course, took place before the OS shipped, before hardware shipped, before the drivers shipped, and before the down-level story was fully baked. So we have a lot of information to share with you today about all those final details when you're looking to adopt DX11 technology or ship titles using it. I also have the privilege of kicking off quite a few talks on this topic for this event. There'll be a lot more deep dives on direct compute, tessellation, block compression, and other things throughout the conference. So I hope you take the time to look into those talks. My talk, I feel, is a bit of a plumbing talk. There's a lot of stuff to cover, but I think it's all pretty essential information if you're going to work with this technology. And I hope I provide enough of a basis if you're not familiar at all and didn't attend any of these talks 2 years ago, or a year and a half. So the really high-level message with DX11 is that it's 10.1 with some additional stuff. So if you're already familiar with D3D10 or D3D10.1, this stuff shouldn't be that unfamiliar to you. If you've mostly been heads down on DirectX 9.0c, a lot of this stuff will be new information to you. The API design, the rendering pipeline is extended, so it's basically the same as the 10 model. We do enable a new set of DX11 hardware features. Obviously, every generation of DirectX, we have to keep up with where the hardware vendors are at. The big difference between 10 and 11, of course, is that we've accumulated a few generations of hardware. When we did D3D10, we did a reset to a known quantity. We had a pretty strong cap standard of what it was D3D10 hardware was, and now we're accumulating again more and more of these feature levels and hardware levels. As the result, we have a broader set of hardware that we support this time around. We support 11 hardware. We still support the 10 and 10.1 hardware. And then we extended a little bit further down than we did with D3D10 for some shader model 2.0 hardware in some limited form, and I'll get into that in a little bit. D3D11 works on Windows 7. It also works on Windows Server 2008 R2, which is essentially the same code base. And then we have a version of it available on Windows Vista as well as Windows Server 2008. And I'll get into all the details of the deployment later in the talk. So this is a little logical diagram of the D3D10 rendering pipeline. It's not that dissimilar from D3D9 if you're not familiar with 10. At the top is where vertex and index buffers come in. You do the vertex shading. D3D10 introduced the geometry shader, which was a new stage that could let you do some primitive-based computations. It may or may not get piped back out to a buffer directly on the video card. Rasterize, pixel shader, output merger is the formal name for alpha blend and stencil and all that. So with D3D11, we've added a couple new optional stages, and these are entirely around the tessellation feature. You don't have to use these, but if you're using tessellation and the geometry shader, you can potentially have quite a few shader stages involved. And there's a talk tomorrow in detail on tessellation. So another way to look at the API is what are the hardware features. If you just ask me what it is DX11 does that you can't do already, there's pretty strong focus on multi-threading. Obviously, multi-threading, multi-core programming is the norm these days, and the DirectX API had never really evolved to really address these issues. With DX11, there was a lot of thought put into how do we make the DirectX render API work better in multi-threaded situations. This feature doesn't require the new hardware. It's emulated if the driver doesn't support it, and there's some interesting kind of levels of support that I'll talk about here in a moment. Direct compute is obviously a huge area of investment. We have a lot of interest in the GPU style computation. A lot of this work has been done by our partners in the past, and there's a lot of good learning there. This feature does require DX11 hardware for the full version, and then after GameFest last year, we announced that there was a limited version available on 10 and 10.1 hardware where the driver updates were available. And again, there'll be a talk later today that goes into detail on these. Then there were a set of features around HLSL Shader Model 5. Every time we do a DirectX rev, we typically have a new version of the shader model. The big focus for HLSL Shader Model 5, other than enabling some of the new hardware features and particularly compute, is around some new constructs for interfaces. There's been a long-standing request from customers for some time to have the CG-like interface. And then some hardware features that go along with that, which actually allow you to do dynamic reconfiguration of the shader without having to recompile it. It's called dynamic shader linkage. As usual, when we add a new construct to HLSL, there's a version of it that emulates on older hardware as best as it can. You can't get the actual dynamic shader linkage feature without DX11 hardware. And then to round out the feature set for DX11, we have the hardware tessellation feature, the hull shader, the domain shader, and then a new block compression format, BC6H, for HDR data, and BC7, which is an improved block compression format for standard LDR data. And there'll be a talk tomorrow morning in great detail on block compression. I encourage you to attend that if you're interested. So the question is, how do we capture all this information? We made a big deal when we did D3D10 about getting rid of caps, and I'll reiterate why that was such a pain again if you're not remembering those conversations. We had to address this in a small way when we came to D3D10.1. A lot of the features of 10.1 were things that didn't make the hardware schedule for D3D10, so we had to add a few more things, and that immediately created a case where not every feature in 10.1 was exposed in original generation cards, and we created this two-level tiering system for the hardware. It was hidden inside the API. Wasn't a lot of splash made about this. When you use the 10.1 API, you can either use a 10.1 feature level, which is the new hardware, or the 10 feature level, which was the 10 generation hardware. Most people didn't pay a lot of attention to this because when they were doing D3D10 or 10.1, they just used the API directly and didn't really look too closely at this feature level stuff. The main difference with feature levels compared to our previous solution, of course, is that it's pretty straightforward and a superset kind of model as opposed to just randomly being able to opt in and out of things. So if you've looked at the DirectX SDK, one of the things we provide in there is a graphics capability spreadsheet, which is this monstrous thing that you cannot read at this point. Just to give you an idea how dense this chart is, here's a blow-up of a little tiny section of it. Across the top are generations of video cards, and across the top to bottom on the side there are the individual cap flags that you have to check. So in the world of D3D9, this worked really well for many generations because you'd have DirectX 5 and you could get a new DirectX and you could use the old hardware and it just kind of kept going and going. But eventually we accumulated so many flags and so many capabilities that you really couldn't be sure what it was you had to support. If you were in the industry making games in the 90s, you know how many game boxes ended up saying, we support these 3 cards, otherwise you're on your own. So one of the big problems here, of course, is not that you have this sea of caps, but that it's really hard to make high-level decisions about it. The new spreadsheet we put out in the August timeframe actually puts these little feature levels at the very top of the spreadsheet. So more or less, this entire chart collapses to those 6 lines. So the problem is not there's a sea of caps, but that you can never really count on it. So typically with Shader Model 2, there were most cards that were Shader Model 2 had a certain set of capabilities, but they weren't really required to. You could have these strange holes in the middle of it where some particular texture blend mode and some particular UV coordinate isn't supported for whatever reason. Sometimes this was just a feature cut. Sometimes they were trying to work around bugs. It was easier for the driver manufacturer to just turn off that cap than it was to address the problem. Sometimes it was a real performance trade-off, and they just felt that it wasn't worth implementing. And then you were in this vicious cycle of either everybody used it or nobody used it because nobody could rely on it. And we did some work around Shader Model 3 generation hardware to try to tighten the spec up. And we made some progress there. So most people doing Shader Model 3 era cards have a rough idea of what it supports, but there's actually no requirement in the spec for any given cap, and you have to code around that. So this adds a lot of axes of development. You have to worry about performance, you have to worry about features, you have to worry about fallbacks, what do you do when it's not there? And we tried to solve this in a clean way with 10 by just saying, well, this is everything you do. There's only a few specific cases that you have to check that are optional. With D3D11, we've had to expand that a bit, but we've tried to keep the flavor of that design of having strict feature levels that makes it easier to organize all this. So the D3D 10.0 feature level, pretty clear, that's everything 10 did. That was shader model 4.0, that was geometry shaders, alpha coverage, all those features. If it's a 10 class hardware and it has the 10 feature level, it does everything that we said it did. The only difference now is that it may optionally support the down level direct compute. 10.1 is the same thing. It's everything that 10.1 did. So shader model 4.1, some of the CubeMap array support, some extended MSA features in the shader, and then optionally a version of direct compute. And then 11 is, of course, every hardware feature we have to offer: direct compute, shader model 5, tessellation, the new compressed format, everything. This is pretty logical, pretty straightforward. If you create a device with feature level 10, then as long as it's a 10 or better hardware card, it's going to work. It's going to work exactly as you'd expect. One of the big differences here from CAPS, of course, is that 11, for the most part, is a strict superset. If you can do it on 10.1, you can do it on 11. You don't have to worry about all these crazy, some things may have gone away. Now, I mentioned that one of the things we did to try to broaden the platform support was to add some limited support for Shader Model 2.0. Now, when we originally did D3D10, we were very clear about what it was we wanted to get out of that API, and we had a very strict hardware standard. We're really trying to address this CAPS problem. When we went to do Windows 7, one of the goals for Windows 7 was to move the desktop from D3D9 to D3D10, and it's actually using 10.1. And in order to do that while still maintaining the exact hardware configuration profile of Windows Vista, we had to have some solution for most newer 2.0 and 3.0 cards. This is not to say that we support every D3D9 piece of hardware out there. As what I was just saying, with the CAPS model, it's possible for something to claim to be D3D9, and it actually means almost nothing. It has a DX7 or better driver. So when one of these feature levels is created, we've evaluated this set of caps. We know exactly what the hardware claims it supports, and that's what you get. So you'll notice that in this stack, not every feature that D3D9 supported is exposed, but the bulk of stuff's here. It's roughly a 2.0 shader model minimum, and then you work your way up. There's a slightly more complex shader model option at the third one, and then there's some things that we can say about whether or not they support event queries or occlusion stuff. Occlusion, a few other features. Now, in addition to the feature levels, there's a couple other things that can change that is a little complicated. You don't have to really think about it in the same way. Typically, with feature levels, that's going to really drive how your content's put together, how you're going to drive the hardware, how you're going to drive the experience, and how high and how low you're going to reach. And then there are a few specific cases that you can think of more as optimizations. With the new driver model that we're offering for vendors, they have about 4 features that they may or may not support. The big one, of course, is BGRA formats. If you're familiar with D3D10, we had a strict RGBA color ordering for all formats. When we added that 10 level 9 feature set, of course, we had to support the older color ordering that many of the Shader Model 2.0 cards require. And in fact, if you have a feature level 9 device, it has to support this feature. It's optional on 10 and 10.1, and it has to be there for 11. There's also a new biased high color mode to make 10.10, 10.2 displays for the new wider gamut displays out there. That itself is optional for 10 and 10.1. It's required for 11, and it's not relevant for the 10 level 9 features. I just said that we're trying to avoid this sea of caps problem, and part of the way this is solved is when you go create a device at a specific feature level, we have documentation that tells you every single thing it has to support, and there are very few specific usage cases that are listed as optional. Most of the time you aren't going to run into them, but if you're using some particular around certain kinds of really large floating point, high precision formats, that may or may not be supported. And the DXGI Programmer's Guide and the documentation has charts for every one of these feature levels that lays this all out. And that includes the new 10 level 9 features. They have a fairly strict set of what formats they support. So in addition to a few of these format changes, there's also this direct compute feature, which may or may not be there for 10 or 10.1 devices. There's double precision shader support, obviously not something most gamers are pushing really hard, but is pretty important for the larger ecosystem doing direct compute. And then the multi-threaded feature, there's some opportunities for the driver to do some better performance things, and we wanted to allow software to react to that and perhaps drive the experience differently depending on whether the driver did that extra work or not. So I'll be talking about a bunch of things around DirectX 11, but I wanted to make sure you understood some of the other terms that might be thrown around when we're talking about DirectX 11. The DXGI library was introduced with D3D10. If you've been using D3D for a long time, you know that every generation of the API, we completely rewrote the way you enumerated devices and created devices, and it was getting kind of tiresome to redo all that glue code. So with D3D10, we introduced a new mechanism for doing this called DXGI, and obviously it was updated to support the new 11 stuff. Traditionally, we've had a driver model on Windows that's evolved a few times, but in this point in sort of the evolution, we refer to the old model on XP as XPDM, or the XP driver model. And with Windows Vista, we introduced WDDM, which was the Windows Display Driver model. And that obviously had to be updated to support these new features. It's a pretty minor rev, so older drivers still continue to work, but some of the new Windows 7 generation drivers can add these new features. There's also a technology that we introduced with DirectX 11 called Warp. Warp is a software renderer. If you've used Ref, you know that it's really slow. It's intended to be something for the driver guys to compare against or for you to verify if it's really you or the hardware. Warp is something more intended for performance work or faster work than you'd want to do with Ref. It's a 10.1 feature level device. It doesn't have any of the optional features I just discussed, but doesn't support direct compute, for example. It is always available if you have DirectX 11. It's a little strange for gaming scenarios. It typically makes most sense where you have an asymmetric situation where you have a lot of compute on the CPU and not much GPU available. Obviously, that's more interesting in the server space. But definitely if you're doing work for offline cooking of textures or you're using these rendering techniques to cook your content, you might find this a useful technology for that. And then over time, as the standard CPUs get better, we'll see how that all pans out. So I've done a lot of talking about the feature levels, and it's always easier to do a demo. It's hard to come up with a good way to demo this stuff. So I wanted to take a moment to show the updated DirectX Caps viewer, and maybe this will make this a little more concrete in your head about what it is we're talking about. So if you've used D3D9, you're probably already familiar with this tool, where you go digging through these display nodes, and there's all these crazy caps and all these groups of things. Every single format has every single usage. This is all the stuff I was talking about, that sea of caps. For D3D10, we didn't do much with this tool because there wasn't as much information to expose, but now that we have these feature levels, there's lots of things going on. So on this system, there's 3 different devices available. Let me see if I can zoom it up a bit. Yeah, this will work. If I can get that out of the So the first three nodes are the hardware devices on the system. There's a ATI Radeon 5800 in this machine, the Warp device itself, which is a software device, and then the traditional reference device. And if you open one of these up, we basically show you the DXGI output information, which is where all the display modes. If this had a multi-monitor setup, you'd see more things there. And then for each of the APIs, we set out and tell you what you need to know that could change from device to device. So for 10, all that's really matters here are these two new optional formats. If you go to the Features tab, this actually summarizes all this stuff in sort of a high-level way. What's the shader model? Does it support this big feature or not? And you'll see the two optional things. This information is derived directly from the feature level, plus that one or two driver caps. There's not a lot of information here that's dynamic in the way that the other charts are. And then just following the 10 spec, this lists the few things that might change. For example, whether or not you support this particular format of really high precision floating point render target was optional for 10 hardware. And then whether or not you supported MSAA and these kinds of things were optional. This is the same thing for 10.1 feature level. So this device is actually 11, so it's capable of the 10.1 feature level. And then this thing happens to show you all the other feature levels in these same kind of summaries. If you just click through them, it'll be pretty clear what it is they can and can't do. Pretty much everything there, most of the things there, fewer and fewer things as you go down the chart. And again, it's roughly the same set of things that are the same from 10 to 10.1 that you may or may not support. Everything else you know has to be supported. 2x MSAA, most of those things are required now for 10.1. For 4, most things are required. And then 8, a lot of that stuff is optional still. And then finally, the 11 feature level. Here is the 4 things I was just saying. 2 multi-threaded features, whether or not you support double precision shaders, the compute shader option when using 10 and 10.1. And then another one of these feature summaries. Obviously, it says yes for everything for 11. On 11.1, most of the things are yes. 10.0, most things, and then it just sort of drops from there. You also see a little more information, if I can get this to pull out. There's a little more information on the 10, 10.1 things because you may be used to the standards for 10 and 10.1. I wanted to call those out. So what are the max texture size, that kind of thing. I think this tool is pretty useful if you're ever wanting to know whether the hardware in your test lab or on your dev machine, what exactly it should be reporting. When you get a new driver from a vendor, you can quickly check out to see if they've added anything. Let's see. And if you look at Warp, you'll see that it has feature level 10.1 for 10.1 and feature level 10.1 for DirectX 11. And then the ref device, of course, basically everywhere you look, it's going to say yes because the ref device supports everything. I found writing that tool and playing around with it made this whole feature level thing much clearer. Try it on a couple of different machines, and you'll have a pretty clear understanding of what the trade-offs are between the different levels. So the DX11 API is pretty easy to understand if you're familiar with 10 or 10.1. It's a pretty straight evolution of that, and I wanted to walk through that to help make it a little more concrete. And you'll see some of the design trade-offs that I'll talk about a bit more. So this is a rough logical diagram. This isn't exactly mapping to the C++ class hierarchy, but it's a good organizational view. You have the device itself, a whole class of objects that are mostly things like the shader objects, queries, in the asynchronous bucket, resources, textures, different kinds of buffers. And then views, which is one of the big things we did with D3D10, where we split resources into 2 halves. You have the data itself as a resource, and then a view, which is some way to either treat it as a render target, treat it as a cube map, treat it as a texture array, things like that. When we did the 10.1 update, we only made a few changes to the API. We added an alternative version of Blend, and a blend state. We added a slightly updated device, which is actually derived from the 10 device. And we added a slightly updated shader resource view. Most of the changes in D3D 10.1 were actually more at the HLSL level when you looked at the shader model. It's worth noting that these changes are here, though, because if you're jumping directly from 10 to 11, these changes also accumulated. So the DX11 version of the API for this part of it is identical to the 10.1 part. So all the same pieces. The shader resource is the same as 10.1. The blend state is the same as 10.1. Then there were a few more changes made to kind of round out this picture. The big one over here is that device is no longer one object. Device is now device and device context, and I'll get into that here in a moment. Otherwise, the device child just has a few more things for the dynamic shader linkage and the new shader stages, and then there's one more view that was added for compute shader. All the really interesting stuff happened in the device. So object creation, all the things that create resources, that create shaders, all that stuff is still in the device, and that hasn't changed. What did change is that everything related to rendering got pulled out into this new interface. So a device context is an object that does all your rendering. And the device itself is just the thing that controls creating resources on the device. So rendering state, mapping and unmapping resources, setting off and ending queries. By default, you always have one device context, which is the immediate context. So if you have an immediate context and the original device, you have the equivalent of the DX10 device. And then you have the option of creating as many of these deferred contexts as you want. This change itself is really the basis of all the work we did for multi-threading, just splitting those things up so that it's much clearer about what the multi-threading behavior should be. Traditionally, we've tried to have thread-safe behavior. It tends to have a bit too much overhead if you do it to the whole device. You could opt into it for DirectX 9. You could opt out of it for DX10. It was kind of confusing, and it was never quite what people wanted. So the reason for the split is pretty obvious if you look at the thread safety rules. The D3D11 device is considered thread safe. You can call it from any number of threads, and you don't have to worry about doing the synchronization yourself. Now, if the driver itself doesn't support these optional features for concurrent creation, then the actual implementation at the runtime will end up taking a coarse lock. The driver has the option of doing much more micro locks here. Also, without the driver's concurrent create support, then effectively anytime you create an object or you're doing rendering on the immediate context, those will have to be excluded internally by a coarse lock. Pretty much all the other objects methods that are derived from D3D child, things like set private data and things like that, those are all thread safe as well. And as always, if you're only really a single threaded app and you just don't want any of this overhead, you want any of this stuff, just you can create the device and force it to a single threaded mode. The device context is not thread safe. It's intended to only ever be used from a single thread at a time. So the immediate context should only be called from one thread, typically your main rendering thread. And then when you create additional device contexts, deferred contexts, you'll usually assign them out and have one thread associated with one device context. It does all its work on that. The one complexity here to keep in mind is interactions with DXGI may not be quite as natural as you might think initially. If you're using DXGI things, particularly like present, that is not concurrent with other kinds of rendering around the immediate context. Part of that is a hidden tie between the APIs. Usually it's not a big deal because your main presentation loop will do some immediate context stuff and then do the present, and it usually works out fine. And as I mentioned, set private data, add ref, QI, those things are all thread safe. So when using the device context in immediate mode, everything's going to go immediately to the device. It all works pretty naturally, just like you're using the old D3D10 APIs. With the deferred context, it's pretty similar. You can just switch out code that's using the immediate context to use a deferred context, and it, in general, just works. All that information is queued up in a command list, and then you can submit that command list to the immediate context for actually presenting to the rendered device. There are a couple of limitations to keep in mind. In order to make this efficient and work well, we're actually recording all this information in the command list. It's not exactly like working with the live hardware. So when you're using map, you can still do that, but you've got to use the discard no overwrite model where you're not getting the old data back because who knows what's on the hardware at that moment. You can't use get data on queries. You can begin and end them and do predication and those kinds of things, but you can't get immediate data back from them. And there's a particular usage mode where you might submit a command list. If you activate a query on the immediate context, you submit a command list, and that command list itself uses the same query, the whole thing's thrown out because it has no idea what you're trying to do. So you can use one set of queries in one context, another set of queries in another, and that works fine. But if you're trying to have this kind of mixed use of the same queries, it can end up being a problem. And to solve that, we just throw it out. If you're using the debug layer, it'll give you informational about that. So to sum up our multi-threading recommendations around this UAPI and where we're at in the space right now, using the concurrent creation features is pretty simple. This is something that people have tried to fake for many years with D3D9. They'll either create an object and hand it back to another thread, or they'll have their own mechanism to try to make this work. And the DX11 kind of solution, just use the device. It's thread safe from your loading thread and your rendering thread, and it all works out fine. It's particularly useful and easy to implement for anybody who already has these loading threads on 360 or D3D9 titles. In general, the runtime emulation is not bad. It's not ideal, obviously, for every kind of scenario, but it works pretty well in practice. It's certainly about as good as the kind of things that you're going to implement yourself. And if the driver itself supports this feature, it'll be a little better. And compared to the D3D10 multi-threaded behavior, it's already improved. The one caveat here in terms of usage, typically when we introduced D3D10, the way you can create resources is either create the resource and pass it a buffer of data to copy into the resource at the very beginning. It's called an immutable. And then never set it again. Most people use the more D3D9-like behavior of creating the resource and then either mapping or updating the resource at some later point. With concurrent creation, it should in general be a little better if you can actually pass that initial data thing to it when you create it. That should be a little more efficient in the multi-threaded scenario. So those P initial data you're probably passing null to all the time. You probably want to go back and take a look at those. The concurrent submission, we're a little early in the adoption of this feature, so it's hard to give super concrete advice about what the best way to go about using this feature is. IHVs and developers are all actively figuring out how they want to take advantage of it and work together and come up with the right solutions. From what we've seen to date, it's got some good scaling behaviors. If you're on a triple core or a quad core situation where you have a lot of CPUs, you can make much better use of them this way. Probably not as useful on scenarios where you only have a dual core system. A lot of those things are already done with existing driver hacks, so it's a little hard to beat that. And as always, one rendering thread per core. You don't really want lots of rendering per core. You don't want to have things kind of sharing each other. There's a thread pool API in Windows Vista and Windows 7, which does a really good job of handling the scaling for you. It's probably better than doing your own scheduler or thread pool for that kind of situation. If you do have your own rolled solution, make sure you look at the core detection sample in the DirectX SDK. We try to handle all the crazy scenarios where computing affinity masks in kind of a dumb way can really mess up your game. From a logical perspective, it's somewhat similar to Xbox 360 command buffers. There's a lot of technical differences, and we're not saying it's a trivial port back and forth. But if you've structured your game in a way to take advantage of Xbox 360 command buffers, you'll probably be able to take advantage of command lists in DX11. Some of this has to do with what data you can manipulate and what state you can change. There are techniques with the DX11 multi-threading where you can get data into the pipe that's different without having direct control over changing all the state. In 360 command list, you have a little bit more low-level hack into what the actual command list consists of. At the moment, if you go poking around in the DXCaps viewer, you'll see that most drivers do not report driver command list support today. So I would definitely suggest contacting your IHVs and find out where they are with it. Maybe get a private driver and try it out. Driver concurrent creates tends to be a little more often enabled in current generation drivers. So if you're looking at your DirectX 10 database or code base and you want to move it to 11, it's actually a pretty straightforward process. I've done it a couple of times. You can probably do it in an afternoon. It's a pretty simple text translation. If you did some 8 to 9 or 8.1 to 8 to 8.1 kind of stuff, it's the same kind of thing. You update some symbols. You will have to fix up for the 10.1 changes if you had a 10.0 and not a 10.1 renderer. Everywhere you're currently using these render calls, you'll have to have two objects. You'll have to have a device context and the device. Sometimes you'll use the device context instead. The simple way to do that is just to sort of transform it to use the context for the rendering calls, and then when you go back to optimize for multi-threading, you'll revisit that usage. There are a few places where things that you expected to be on a different object have moved. So things like map and begin in, get data, those things were associated with the resource or they were associated with the query object. They're now on the device context. So sometimes you'll need the device, sometimes you need the device context, sometimes you need the query object, and that can change some of your parameter structures a little bit. Anywhere you create a shader, you'll have to throw an extra null on the statement for this new class linkage feature. You're not using it initially, obviously. And anywhere you set and get a shader, you have a corresponding null to the instance object that would have gone there. And there's a topic, migrating to Direct3D 11, that lays all this out in a nice table form if you want to just kind of automatically do it with somebody. For the most part, I didn't run into a lot of problems here. There was one particular little change that I noticed might catch some people up. The D3D10 resource miss flag got redefined a bit more in 11 than I was expecting. So if you're using any magic numbers, you might run into some strangeness. As long as you're using the pound defines, it should be fine. There is one minor API feature that disappeared, and that's this text filter size. This was added mostly for the desktop to use. I'm not expecting a lot of games to run into this. But those APIs just disappeared between 10 and 11. If you are using these APIs, I would suggest looking at a technology called DirectWrite, and you'll see some of that stuff over in that API. The one other thing that changed was there was a set of vendor-neutral performance counters defined for D3D10 in the header, and as it turned out, they were pretty inconsistently implemented, or they weren't implemented at all, so they were just cleaned out. More or less, all performance counters are vendor device dependent right now. If you've been staying in the world of D3D9 and haven't looked at all at 10 or 10.1, moving to 11, you've got a lot of work cut out for you. It's everything that we said to do for moving from 9 to 10. More or less, you're just going to move from 9 to 10 and then move a few extra things to 11. That means removing all fixed function pipeline stage usage. There's a sample in the DirectX SDK called fixed function emu, which has some nice sample code to do all this. State management has to be switched over to immutable objects. This is something that catches a lot of people up. It has a pretty big impact on the performance characteristics, and if do it right, you can get a good win out of it. And we've even seen some games that have done this work at an architectural level, and then it improves their 9 renderer too. There's some more strict rules about how shaders link up and how shader layouts work. Some kind of sloppy dynamic content, particularly art-driven pipelines, can run into this as a problem. And you actually have to have the input layout when you create the shader object. Sometimes the ordering can be a little messy if you're using D3D9 code. You need shader resource views in addition to texture resources in order to actually capture what you need to bind to the pipeline. Moving to the DXGI formats can be a challenge for some people around their content. The strict RGB order caught up some people. You can't really rely on it being there. It's optional for the new BGRA support. The 16-bit formats, 24-bit color formats, you have to do some work in the way you load your content to make sure it all matches up. And usually the biggest challenge was just the way constant data was handled. You have basically a shared resource in D3D9, and you tend to pump a lot of information through that. And if you map that to a single constant buffer where you're doing the same thing, you end up paying maximum overhead, and you lose all the benefits of the constant buffers. And that was usually what killed performance on initial kind of naive ports. So while it might be a little daunting, the good news is that we have a lot of resources to do this. So all the guidance we've been giving for years on moving to D3D10 from D3D9 is fully applicable to 11. So we've got some great presentations, we got some great resources. Shannon Drone's GameFest 2007 talk is sort of the seminal performance pitfalls version. All that material still applies to 11 just like it did to 10. And if you haven't looked at this stuff, definitely recommend you take some time to review it. Great guidance, and it should all be applicable. So I wanted to round out the talk with some sort of tidbits of information, certainly useful details of where you go looking for different things that may have changed since D3D9. So the HLSL compiler is how you get all your shaders written. You don't write shader assembly in 10 or 11. We used to have the stuff delivered mostly through the D3DX library. And with DX11, we put it into its own DLL, D3D compile DLL. You don't have to use D3DX at all. You can go directly to this DLL and do all your shaders there. It is used indirectly by all these other APIs too. It's in its own Redist folder if you end up wanting to do this on users' systems, although we do recommend offline compilation if you can do it. And the dynamic shader linkage feature actually should make that a little more feasible for some hardware. The current generation compiler is an extension of the one we've been using for several years. It supports all pixel shader models, all vertex shader models. The only thing that it doesn't support is the old 1x stuff. And this is a fairly complete list of profiles that the DX10, DX11 generation stuff. You have vertex, pixel, geometry shaders, compute shaders, hull shaders, domain shaders. And then you have these new special ones for 10 level 9, which I'll talk about briefly. So one of the things that we did a lot of work in when we started with DX10.1 and we did with DX11 was to try to make it a little easier to do this. If you were using 10, every shader had to be 4.0, and that just worked fine. With 10.1, you can use 4 or 4.1 shaders on a device. With 11, you can use 4, 4.1, or 5. You can use any mix of them. It makes it much easier to just set this stuff to the device and not worry about it. In general, you should try to use the lower profile, because if you're using 4.0, you know that's going to work on a broad set of devices. Clearly, if you have a 4.1 shader, you can't apply it to a 10 feature level device. You can't go down. So one of the tricks in order to make this 10 level 9 technology work is you really have to have both a 4.0 and a 2.0 version of every shader in order for the rendering pipeline to actually work, because under the covers, we're using D3D9 for those devices. And this is accomplished with these special profiles, which are actually internally compiled twice. This makes it a little complicated to write, because you have to follow some of the limits of 2.0 to make this work. It can be a little trial and error to see whether every shader you've written can support this. I don't know how much time I would focus on this at the moment, but when you start looking at this technology, keep this in mind. So here's a diagram what I meant by you can always go lower. It's pretty easy to map it. So we always recommend using the latest compiler. There's always performance work and optimization work going on. If you're using an older compiler, you're probably missing out on a lot of stuff. It's pretty important to avoid the inbox compiler. It's basically the HLSL compiler as of December 2005, something like that. And it hasn't been updated since then. And as always, if you can use lower profiles, you'll probably have a broader feature level set. So if you're able to have your entire game written in 9.1 shaders that would work on all devices. It's unlikely, but it might be true of some portions of your game. For direct compute, we tend to flip that advice. If you can use the higher feature level, that tends to be much more efficient. So you might have to do some extra special casing in there to make that work. And as always, you much prefer compiling your shaders offline. Ideally, you never compile shaders on an end-user machine. Sometimes that's unavoidable. But in general, this translates to incredibly long load times, which is kind of a pain. You can pay for it once in the build time and save millions of users lots of pain. If you've looked at the effects library in the past, this thing has gone through several generations as well. It tends to evolve with the API. The goal is still the same, which is to simplify some of this complexity around managing constants and buffers and resources and shaders and all the binding necessary to make that happen. The effects for D3D11 is effectively the updated version of 10. It's a shared source in the DirectX SDK, so it's no longer something you can't get source to. It's right there. You can take a look at it. You can use it as sample code. You can use it to make your own versions. You can use it just to make your own kind of fixes and optimizations. The original FX9 was closed source in D3X9, and then there was lots of feedback that it was kind of painful to have that dependency. So with D3D10, FX10 was moved into the OS, and then we had another set of problems of not being able to really service that quickly. So we're hoping that this third stab at how we provide it to you will work out, provide the best good example code, useful as is, and still not block you from making progress if you run into issues. If you have existing FX10 code, moving to FX11 is pretty trivial. About the only thing that we didn't carry forward was the effects pools. Most people tended to use it in a way that really wasn't what we intended, and it's not clear that effects pools had as much use as we thought it did. Moving from FX9 to FX11 obviously is a pretty big jump. And the guidance we've given in the past will all apply. And they're, of course, matching HLSL profiles for all this stuff. FX2, 4, 4.1, and 5. There's also been some changes happening with the D3DX utility library itself. If you've been using D3DX9, you know it ended up kind of being a kitchen sink DLL with lots and lots of stuff in it. DX10 is a little simpler, and DX11 is a little simpler still. Part of this is driven by the feedback we get from customers that there's just too much dependencies. Nobody really likes the deployment of it. At the same time, there's a lot of useful stuff to make things happen in there. So the primary thing D3DX11 does is all the texture loading. There's some asynchronous loaders to make it a little easier to take advantage of multi-core systems for this loading. It does not include math, mesh, sprite, or font. So if you're using any of those technologies, you'll want to look elsewhere for alternatives. I'll talk briefly about the math alternative in a little detail. Otherwise, the DXUT 11 implementation probably has what you need there. One comment, D3DX 11 DLL as it is right now, when you're using these new BC6H, BC7 texture compressions, is using a CPU-based algorithm. And once you'll attend the block compression smorgasbord talk, you'll understand why this is a monstrously huge search space. And it can be pretty slow. Large textures, it can take minutes, maybe longer. So if you're looking at the new texture compression formats, we highly recommend you take a look at the encoder-decoder sample in the DirectX SDK. This has a GPU implementation of it, which does it pretty fast. And that relies on Compute Shader 4X, so it works on 10, 10.1 hardware, as well as 11. So while we've been trimming the D3DX utility down, there's been some investment in a different set of utilities around trying to make compute a little easier. Compute is a pretty complicated space, so we wanted to provide some basic stuff that you could make use of immediately. So there's an optional DLL called D3D-CSX, and this contains some direct compute functions. Right now it requires DX11 hardware. We're looking at what we can do to bring some of those features down level to CS40. CS41. So there's a scan function and an FFT that are all GPU implemented. You might find that useful, particularly on the content production side of things. And as with these other DLLs, it's an own cab, so you can kind of decide whether you want to redist it or not. So I mentioned this technology called XNA Math. I have to admit that I'm sort of in a branding quandary right now. XNA Math is just Xbox Math. If you're familiar with the Xbox 360 XDK, there was a library provided early on by the graphics team, and that does some great C++ SIMD stuff optimized for VMX 128. So what we did in, I think it was the March of last year, we have a version of this library that supports SSE2. So it's the same library, same API, and then we added some new functions there. This is pretty good for making cross-platform SIMD code. You can write it once, and it'll compile pretty optimally on both Xbox and Windows. We did a lot of work with Visual Studio 2010 to get them to really improve their intrinsics implementation. This works on 32-bit, 64-bit native. There's a no-scaler version for you to do some fallback testing and maybe performance testing. It's got all the usual stuff you'd expect for graphics. It isn't a full mapping to everything SSE can do because we're really focused on something that works well on Xbox as well as Windows. And it's all header implementation, so you can use all that source as reference as well. It has a lot of stuff for doing packing to and from graphics formats, a lot of the typical matrix, linear algebra, vector stuff. It does make some assumptions about alignment. It does make some limitations. So if you're using D3DX math, it might not map exactly, but functionality-wise, it's pretty close. For the February 2010 DirectX SDK that we just released last week, I actually added a documentation page which explicitly covers porting from D3DX math to XNA math, if that's where you're at. The one thing I would say is if many of the large studios have given us feedback that they have 5 math libraries in any given product. Not all of them are really optimized. I would highly recommend looking at your project and where your math solutions are and consider this as something you might try to standardize on. And now we're in the real plumbing material that I'll try to wrap up. So when we do DirectX 11 and it's associated with the new Windows 7 OS, there's not much to say. It's just built in. You don't have to worry about it. But in order to really reach the broad market, there has to be some way to reach Windows Vista users. And we have a way of getting the DirectX 11 API down level onto those machines. It's worth noting that this is distinct in the runtime. So one of the things that's confused people who've been doing deployment for DirectX for years is it used to be that when you ran direct setup, we installed everything on any OS that you were on, and you didn't worry about it too much. There was a shift around Windows XP where the core runtime is actually part of the OS. So Direct 3D, Direct Sound, Direct Input, pretty much by definition, direct setup never installs those things. If you're on XPSP2 or better, that's already there. We do still install all these optional things, these DLLs, D3DX 11, D3 Compile, D3 CSX. So if you use any of those technologies, you're going to have some kind of use of the direct setup redist. Xaudio 2, Xinput, all those things. This also has the side effect of if you install the DirectX SDK today on Windows Vista, you will not have DirectX 11 as a result. You'll have all these optional bits, but you aren't going to get any runtime bits. Those have to be serviced through the OS solution, which I'll get to in a moment. More than likely, you already have it on your system. You just don't realize it. The DirectX SDK does install the debug layers. It does install the reference device. So it's still worthwhile installing it. So when I talk about the DirectX runtime, I spend a lot of time on news groups and mailing lists trying to explain what we mean. It's a bit of a shorthand, and it's lost some of its meaning now that it's not something that's strictly part of the separated from the OS. But for what I'm talking about in technologies for DirectX 11, it's obviously D3D11. That API is part of the runtime. The DXGI 1.1 library version is clearly part of this runtime. You need it. the Warp 10 driver for software, the 10 level 9 driver, Direct3D 10.1 being updated to support these new feature levels for Warp and 10 level 9, that's all included. And then these Direct2D, Direct-Write technologies are also in this package. So when I say DirectX 11 runtime, I mean any and all of this stuff. The way all this stuff ends up on Windows Vista machine, it's all included in Windows 7, it's all included in Server 2008 R2, but it ends up being deployed through Windows Update for Windows Vista. The KB number is up here. You have to have SP2 installed or it won't be available for your system. So RTM and SP1 won't have this. The good news is that pretty much everybody has automatic updates on, and they probably already have this installed. It's already on their system. They took SP2 automatically a long time ago. There wasn't a EULA involved. Of course, anyone working in installation or setup knows that the 90% case isn't interesting because you aren't going to get a support call from that. What you're worried about is all the edge cases. In order to make sure we had pretty clear coverage of this, there is an article in the DirectX SDK that covers the entire story, everything that could go wrong, everything you have to worry about covering, and we wrapped it all up in a sample. The sample's localized, it's ready to use. It's pretty simple. Just point your installer folks at it, and it should be pretty straightforward. There'll probably be a future service pack where it's just rolled in, and we won't have to worry about this anymore. And in general, if you have a user that's still on RTM Vista, you're probably already having servicing problems, particularly around the VA space issue I talked about a few years ago. So it's not really that burdensome. Just something you have to be aware of when you're doing your deployment. Now, the one mess in all this, something that is a little frustrating to game developers, is that the corporate world is thought of differently by Windows than the consumer world. So the previous update that I just told you works perfectly fine everywhere in the world unless you're inside a large corporation. In those situations, the Windows Update system is actually managed locally or potentially managed locally, and there's a different update that has to be approved by that person in admin to make sure that these bits end up on your Windows Vista machine. So if you're a developer and you're inside a large corporation and you're using Windows 7, none of this matters to you. But if you're inside a corporation running Windows Vista and you have one of these weird local managed servers, you've got to go tell your local admin, I need you to approve this update or I can't do DX11. The February 2010 DirectX SDK version of that article I just mentioned spells all this out. So you can just cut and paste that and mail it to somebody. So we're getting close to the lunch hour. I'll try to wrap up here. So in general, if you have a 10.0 or 10.1 code base, moving it to 11 is pretty straightforward. You will have to make sure that your installer folks are aware of what that implies and make sure that they handle that properly so that you don't get support calls from it. But technologically, it's a very straightforward change. If you have a Windows Vista, Windows 7 only title, and you're not really worried about targeting on older hardware or older OSs, then the 10 level 9 feature level is going to be pretty useful because you won't have to have a 9 feature path to reach the broad set of Vista users. Not so interesting to the hardcore, but certainly for more breadth reach, that technology has a much broader set. And this maps to effectively everyone who has the new desktop on Windows Vista or Windows 7. It's that set of cards. If you still need Windows XP title support, which obviously a lot of people still do, clearly the legacy D389 path is a little clearer, a little more straightforward. You will have to deal with some potential app-compat behavior differences between Vista and Win 7 and your XP legacy path, but there's not a lot of need to implement 10 level 9 if you're going to be rendering through D389. That said, it can be pretty useful for internal development purposes, for reproing bugs, for looking at different options, having a broader hardware set. So you may find the 10 level 9 feature levels useful to implement internally, whether or not you ship it to end customers in the short run. In the long run, we expect most people will probably end up standardizing on something like DX11 for the broad set. So if you still only have a D389 legacy code path, this is a good time to get in on an update, do a technology refresh. A lot of the features that we introduced in 10 and 10.1 are there now in 11. The deployment story is quite a bit more tolerable than it was for 10 for many of the marketing folks. You have a lot of existing resources out there. All the IHVs, all the material we've put out is all there and ready to go, so you're not in a bleeding edge kind of situation where you were with 10. And by moving to D3.11, you get the latest hardware features and all the new things coming out of various people, AMD, Intel, NVIDIA. You get all the access to the existing 10 features that maybe are latent right now because you're using your 9 renderer and you don't have access to those features. And then we have this broad set of support if you are interested in reaching to the broad set for pretty much anybody who has a WDDM driver with Windows Vista or Windows 7. The latest DirectX SDK is where we'd recommend you go. Currently, that link points to the August version. We'll try and get that fixed to the February version. But August has everything you need to do this 11 work. Of course, all the GameFest 2008 presentations that were put out, all that material is still quite relevant. And then we have a whole slew of talks coming up the next couple days, the next day, later this afternoon, tomorrow afternoon, and tomorrow morning, as well as all the talks from AMD and NVIDIA. They're here in the expo hall, so I would definitely take some time to talk to them and see where they are with their hardware. So I'm going to go ahead and end it there. I'm a little over. I will point out that this deck, when it gets posted, there are some code samples that spell out some of this stuff. And probably the most important thing is a section on the debugging story. It's changed quite a bit from 9, so I would definitely take some time to read through this. And this is the magic undocumented feature that we keep trying to get documented. That'll let you get a lot more information out of the debug channel. So take a look at the appendix when this comes out, and you'll find some good stuff there. I'm available for the next 10, 15 minutes if anyone wants to come talk to me. Thank you very much.